of a proof involves this beautiful quantity called the Lagrangian. Okay, so it's going to appear like magic, but of course, when you see the logic, it's actually the logic that comes first and then the Lagrangian follows. Okay, but I'm going to present the Lagrangian first. Okay, so proof. Okay, so the first thing we're going to do is introduce this thing called the Lagrangian. Okay, and if you want a mechanical prescription for introducing the Lagrangian, you take the objective, the thing that you're trying to optimize, and for each constraint you introduce a Lagrange multiplier, and you formulate the constraints in the form of something less equal to 0. Okay, you multiply by your Lagrange multipliers. Okay, and you add that to the objective, and that becomes your Lagrangian. So your Lagrangian L, which is a function of your weights W, your bias B, and then you introduce these Lagrange multipliers, which I talked about earlier, these alphas. Okay, and the alphas are positive, non-negative, sorry. Okay, let me just introduce this function. You can argue with me, I'm defining a function. Okay, so this is 1/2 W transpose W. Okay, now plus for each Lagrange multiplier, sum over n equals 1 to big N, alpha n, 1 minus yn W transpose xn plus b. Okay, so that's the Lagrangian. And you will notice that what I've done here is I've put the constraint in the form something less equal to 0. So, this constraint here, can be written as 1 minus yn W transpose xn plus b is less equal to 0. Okay, and so I place that constraint in here. Why the less equal to 0? Why didn't I formulate the constraint by taking the 1 to the other side? That has to do with the fact that I'm requiring the alpha n's to be non-negative. Okay, now I'm going to show you the high-level argument, not the rigorous proof, the intuition behind why. Okay, if we can optimize this guy, okay, we will have a solution to this problem. And so the idea here is that we're going to minimize this guy, minimize the Lagrangian, minimize L, okay, with respect to our original variables, W and B, unconstrained, and simultaneously maximize L with respect to the alpha n. Okay. So it's a saddle point optimization problem. So we have introduced a function, can't argue with me. And I'm claiming that if we minimize this guy with respect to my original variables and maximize with respect to my Lagrange multipliers, but they must be, non-negative. Okay, here's the claim. If I solve that problem, okay, I will have a solution to my original problem. Okay, the W and B that come from this saddle point problem will be a solution to this problem. So solving this problem, solves the primal problem. Okay, and so let's prove that. And I'll put this in quotes because it's not the rigorous proof, it's just a high-level intuition. Okay, so let's look at what it takes to solve this problem. So we're going to solve this problem, we're going to output, W's, B's, and alphas. Okay, and the alphas have to be positive. Now first, let's look at the constraints. So let's look at this constraint. Okay, in order to solve this problem, I must minimize the weight subject to this constraint. Okay, so there are two situations. Either this guy, is less than or equal to 0, okay, or it's greater than 0. So either 1 minus yn W transpose xn plus b is less equal to 0, or 1 minus yn W transpose xn plus b is greater than 0 when I've solved the problem. Okay, so you can take every n and ask this question, is it less equal to 0 or is it greater than 0? Okay, so for each n. So let's consider the case where 1 minus yn, okay, W transpose xn plus b is greater than 0. Okay, so if this is the case, remember I'm maximizing with respect to alpha n positive. Okay, so if this term is positive, then alpha n 1 minus yn W transpose xn plus b, okay, is positive, because this term is positive and this is greater equal to 0, and I get to manipulate these guys in the optimization problem. The whole idea of an optimization problem is that I'm trying to find the alphas that perform this optimization. So if this is positive, what will be the optimal choice for the alpha n, that particular alpha n? No brainer, since I'm trying to maximize L with respect to the alpha n's, I will take this guy to infinity. Okay. And the Lagrangian will attain an infinitely large value, okay, because I'm trying to maximize with respect to the alpha n. And the only thing that will prevent that, okay, is if this is not greater than 0. But you know what would sort of encourage me to set this not to be greater than 0 is that, you know, I have competing goals. I get to choose the w's, and I'm going to pick w's to minimize the Lagrangian. So I'm going to pick w and b to minimize the Lagrangian. Okay. So the goal of picking w and b is to minimize the Lagrangian, which competes with the goal of picking the alphas, which is to maximize the Lagrangian. Oh man, tug of war here. Okay. But, you know, as I'm trying to optimize w and b, I will notice, if I set this greater than 0, I'm going to get an infinite Lagrangian. Since I want to minimize the Lagrangian with respect to w and b, I had better set this to be less than or equal to 0. Okay. Because, so, in other words, this process of minimizing with respect to w and b, maximizing with respect to alpha, is going to result in this quantity at the optimal always being less equal to 0. Otherwise, it can never be optimal with respect to w and b, because w and b is trying to minimize the Lagrangian. So, at the optimal, okay, 1 minus yn w transpose xn plus b greater than 0 will not be possible. Because then the Lagrangian will be infinity, and so it's not optimal for minimizing with respect to w and b. Okay, so that will never happen, which means that this will never happen. So when I solve this problem, it's going to be the case that for every n, 1 minus yn w transpose xn plus b will be less than or equal to 0. So at the optimal, okay, 1 minus yn w transpose xn plus b will be less equal to 0, which implies that yn w transpose xn plus b will be greater equal to 1. Take this to the other side. But that means that when I've solved this problem and produced weights w and b, I don't even have to look at the alpha n, okay, because I don't technically need the alpha n's. I just want w and b. When I've solved this problem, it will be the case that the data is separated. So at the optimal of this problem, the data will be separated. So at least we see that some pieces of this original primal problem are now starting to appear. When you solve this problem, the data will be separated. Okay, and okay, so now let's look more closely at this term, alpha n 1 minus yn w transpose xn plus b. So there are two cases. We know that this will always be the situation. So either 1 minus yn w transpose xn plus b equals 0, in which case the contribution to this sum for that value of n, for that term, is 0, or 1 minus yn w transpose xn plus b is greater than 0. But since I'm optimizing with respect to alpha n and trying to maximize, okay, the quantity alpha n 1 minus yn, will be less than 0. The quantity alpha n 1 minus yn w transpose xn plus b will be less than 0, or less than or equal to 0, because alpha n is non-negative and this is strictly negative. Okay, so if this is strictly negative, okay, then this quantity is less equal to 0, and since I'm trying to maximize with respect to alpha, the best I can do is get it equal to 0 by setting alpha n equal to 0. So this will imply that alpha n is equal to 0 at the optimal. Okay. In which case, either this term is 0 or that term is 0 at the optimal, and so this sum is 0. Okay. So let's summarize what we have learned. And what we are about to summarize are what are called the Kkt conditions. Okay. So at the optimal. So at the optimal, alpha n 1 minus yn w transpose xn plus b is going to equal 0. So this means that either alpha n is equal to 0. So this means that either 1 minus yn w transpose xn plus b is equal to 0. Okay, which means that, this means that yn w transpose xn plus b is equal to 1. That's exactly the support, that's exactly the vector who's on the margin. Okay, 1 is the margin. Okay, and beyond 1 is strictly bigger than 1. Okay, so these are the points that end up on the margin, what we used to call support vectors. Okay, so this guy, xn, is a support vector on the margin. Okay, so either that is 0 or the other term is 0, or alpha n is equal to 0. And the Lagrange multiplier for that data point is 0. Okay? And so that data point is essentially useless, but we won't treat data points as useless. All data points are useful. Okay? All right. And at the optimal, okay, the Kkt condition that this is equal to 0 means that this term is 0. And so the Lagrangian L star is equal to 1/2 W transpose W. But what does that mean? It means at the optimal, the quantity that we have minimized with respect to W and B is exactly the quantity that we want to minimize. Okay? And we will therefore have minimized it with respect to W and B, subject to the constraint. Because we just proved that all these constraints are valid. Okay? So at the optimal, L star equals this will have been minimized with respect to W and B. And we already proved that the constraints will be satisfied. Y and W transpose X n plus B will be greater than or equal to 1 for each n. We proved this, that the constraints will be 1. And we also have this additional Kkt condition which says that any constraint which is not saturated, which is not equal to 1, will have a 0 Lagrange multiplier. Wow, we proved all of that. But didn't give the rigorous proof, we just gave the high-level intuition. Okay, almost a proof. Okay. And so, essentially, okay, what we have shown is that this Lagrangian is intimately related to the original problem, in the sense that if you maximize with respect to L, and minimize with the Lagrangian with respect to W and B, and maximize the Lagrangian with respect to the alphas, you recover a solution to the primal problem. And so all that remains is to actually perform that optimization. So let's do that. Okay. So let's perform that optimization. And then we will be done with the proof. We will have the proof. Okay. It turns out that when we perform this optimization, okay, we will derive exactly this problem. So in other words, I'm now going to massage the minimization of L, maximization of L, okay, with respect to different sets of parameters. I'm going to prove that solving this problem is essentially amounting to solving this problem. And so then this problem is equivalent to this problem is equivalent to that problem, boom, this problem is equivalent to that problem. And the only thing that will remain is a few minor details to show how when we solve this problem and get the alpha n's, we can recover the optimal W and the optimal B. Okay, so let's prove it. Let's finish it off. Okay, so here we're minimizing a function with respect to some variables, unconstrained. We know how to do that. We set the derivative to 0. So the derivative of the Lagrangian with respect to the weights is equal to, okay, so let's take the derivative. Derivative of the quadratic term is just W. 1/2 W squared, it's W transpose W, but so 1/2 W squared becomes W. Okay, plus, there's a linear term. Okay, so there's a linear term in here. So the derivative of the linear term is a derivative of a sum of derivatives. So we take the sum of alpha n, yn, W transpose xn, that's the linear term. So the derivative is just the coefficient xn, yn, alpha n. So plus of a sum from n equals 1 to big N, alpha n, yn, xn. And we must set this derivative to 0. So this must equal 0. Okay, so let me put it. That's what the derivative is. We must set it equal to 0. So this implies that at the optimal, W will equal, I forgot the minus sign. There's a minus sign here. There's a minus sign here. At the optimal, W will equal this quantity. the sum from n equals 1 to big N, alpha n, yn, xn. Let's take the derivative of the Lagrangian with respect to b. Okay. Well, there's no b dependence here, so that's 0. So now we have a linear term, alpha minus of alpha n, yn, b. Okay, so the derivative is just the coefficient alpha n, yn, okay, with the minus sign. So we get minus the sum of from n equals 1 to big N, alpha n, yn. Okay, and we must set this derivative equal to 0. So this must equal 0, okay, which implies that you can ignore the negative sign, which implies that sum from n equals 1 to big N, alpha n, yn equals 0. Okay? So, the stationarity conditions for minimizing the Lagrangian with respect to the unconstrained variables is that the derivative must be 0. That gives us, equations that must be satisfied at the optimal. So we can use these equations, plug them back into the Lagrangian. So plug back into the Lagrangian. Plug back into Lagrangian. Okay, now I'm going to ask you to verify for yourself. I'm going to do this very quickly, okay, because we don't need to focus too much on algebra. Okay, so when you plug this guy into the Lagrangian, so this sum is 0, okay, and this sum appears here, sum alpha n, yn, b. The b is a constant and can be pulled out of the sum, okay, and since that sum alpha n, yn is 0, the term with b disappears. Okay, so the Lagrangian becomes, so now we're plugging in these requirements into the Lagrangian, it becomes a function of alpha. So the Lagrangian of alpha becomes 1/2 w transpose w. Okay, so w is this guy, so 1/2 w transpose w. So 1/2 w transpose w is just 1/2 this guy times transpose times itself. So the sum from n equals 1 to big N, from m equals 1 to big N, okay, alpha n, alpha m, yn, ym, xn transpose xm. Okay, so this is this guy transpose times itself. Okay, but you have to remember that this is a sum. So when you multiply it by itself, you have to use a different summation index for the other term. Okay, and so that's why I have two summation indexes, n and m. Okay, and then I have plus the sum of alpha n, okay, plus the sum of alpha n, okay, minus the sum of alpha n, yn, okay, xn transpose w, minus the sum, okay, from n equals 1 to big N, alpha n, yn, xn transpose w. But w is just the sum over, let's use the index m equals 1 to big N, alpha m, ym, xm. Okay, so you see here, this is just minus the sum over n, the sum over m, alpha n, alpha m, yn, ym, xn transpose xm. We have that same sum above, alpha n, alpha m, yn, ym, xn transpose xm. So this sum and this sum are basically the same sum, not basically, they are the same sum. Except this is 1/2, this is minus 1. Okay? So 1/2 minus 1 just gives me minus 1/2. Okay? And I don't need this term anymore. That combines both of these terms. Okay. So what have I done? No magic here. This is just technical algebra. I took the stationarity conditions for my unconstrained variables. They imply certain constraints that have to be satisfied at the optimal, and plug those constraints back into the Lagrangian. Okay, this is a standard procedure when you do constraint optimization. Okay, and now I just massaged, I looked at I did some algebra to see what does the Lagrangian become. It becomes a function of alpha. Okay. And this function of alpha no longer has any dependence on w and b, because these stationarity conditions are used for the exact purpose of getting rid of w and b from here. Okay. And so now I need to continue by maximizing this Lagrangian with respect to alpha. That's what the goal was, to maximize. Okay, so I need to maximize this guy, okay, with respect to alpha, subject to alpha is greater or equal to 0. But I also have this constraint that alpha must satisfy now, that popped out of the the stationarity condition for B. I must have this constraint that the sum from n equals 1 to big N of alpha and yn must equal 0. That's this constraint. Okay. But maximizing this guy with respect to alpha is exactly the same as minimizing the negative of that guy with respect to alpha. So minimize the negative of that guy with respect to alpha. Minimize with respect to alpha. The negative of that guy is exactly this guy. Subject to the constraint and the non-negativity requirement on the alphas. Proved. So I've just proved, or I've just derived, that this optimization problem is essentially equivalent to the problem of, minimax optimization of the Lagrangian. And we already saw that the minimax optimization of this Lagrangian is equivalent to solving the primal. End of story. Proof. Done. Okay. So let me erase the proof. Okay. The only thing, the minor technical detail that remains is okay. So when I solve this problem, I get the alphas. So solving this problem, gives the alphas, let's call them alpha and star. Okay. So how do I recover the W's and the B's? Well, we already know W star, that was part of the stationarity condition. W star is the sum from n equals 1 to big N, alpha n star, yn, xn. Okay. The complication is how do we get B star? Because remember, when we did the derivative with respect to B, we just got a constraint on alpha that the sum of alpha and yn must be 0. Okay, that doesn't give us B. Usually we plug back into those stationarity conditions to get my unconstrained variables, and that's what we did for W. Okay. To get B, we have to actually look at the Kkt condition. This is called the Kkt condition. So if alpha is not 0, if any alpha n is not 0, let's call that a support vector S. So if alpha S is not equal to 0, so if alpha S is strictly positive, okay, then what do we know? Then we know that this term is 0. So ys W star transpose xs plus b is equal to 1. So this guy is a support vector on the cushion. And if this is satisfied, well, we know W star now. We've just computed it. Multiply both sides by ys. Since ys is plus or minus 1, ys squared is 1. And so we get that W star transpose xs plus b is equal to ys. Multiply both sides by ys. Okay. That tells me that b is equal to ys minus W star transpose xs. Bam. Bam. So you've solved this problem and gotten the alpha stars, and now I do a few manipulations and I can get my optimal W star and my optimal B. Okay, so let's erase the proof. So this is just the proof of the equivalence. And as usual, when we do a technical derivation, let me now come and wake up. Okay, because sometimes you are not interested in the technical derivation. So I personally do not believe results unless I see the technical derivation. Okay, so if you fell asleep for the technical derivation, it's now time to wake up. Okay, and listen to the summary. The summary is that the primal problem and the dual problem are equivalent. If we can solve the dual problem, we get a solution to the primal problem. We're going to focus on the dual problem and see how that allows us to go to infinite dimensional spaces. And that's magic. So it's worth waking up for. Okay. But before we do that, let's do an example in the dual version of the problem and sort of just see that yes, indeed things work, and then we will link this dual problem to being able to move into infinite dimensional spaces without any computational issues. Okay, and that's the main goal of today. The miracle of the day. Learning in infinite dimensional spaces. Wow! Okay, so I've reproduced here the example that we solved last time when we derived the optimal hyperplane. So we have these data points, okay, and this is 0, 0, this is 2, 2, and those are both negative, red x's, and this is 2, 0, and 3, 0, and those are both positive. So -1, -1, +1, +1. Okay, and last time and in general, the signed data matrix is also a useful matrix where you take each of your data points and multiply by the corresponding y value. Okay, so the signed data matrix is 0, -2 here because the y's are -1, and then 2, 0, 3, 0. Okay, so that's the example that we solved, when we derived the primal problem, and we saw before that the optimal hyperplane that gets the maximum margin, satisfies the equation x1 minus x2 minus 1 equals 0. Okay. So now let's get that same solution just as an example using the dual problem. Okay. And when you formulate this dual problem in this matrix form, okay, so it looks like a quadratic program. So let me remind you what's the general quadratic program. So a quadratic program. Okay. So what is that? That's minimize over your optimization variable u, which is a q-dimensional optimization variable of u transpose qu plus p transpose u, subject to au is greater or equal to 0. Okay, so now, in our example, q is g, and the components, the mn component of g has to be, the nm component is yn, ym, xn transpose xn. Okay, so it turns out that if you work it out, so this is x sub s. Okay, so x sub s transpose the nm component, where x sub s is the matrix that's formed by y1 x1 transpose, y2 x2 transpose, okay, and so on, yn xn transpose. Okay, so if I do xs transpose, okay, so what is that? This is xs, which is y1 x1 transpose, y2 x2 transpose, all the way to yn xn transpose, times its transpose. So that's y1 x1, y2 x2 to yn xn. Okay. So if I want the nm component, I take the nth row here. So I take the nth row here and the mth column here. Okay. And I multiply this nth row with that mth column. I have here yn xn transpose. Here I have ym xm. So this is yn ym xn transpose xm, okay, which is exactly this term. So if I call this matrix, if I call this G and M, then G is exactly the matrix XS transpose. Okay. So in this formulation, the quadratic form, the matrix that is involved in the quadratic part of this objective is exactly XS transpose. Okay. So this is Q. So mapping this form to the standard form of a quadratic program, Q is equals to X, the signed data matrix XS transpose. What is P? So that's the linear term. So the linear term is -1 transpose. So P is -1 transpose. Okay. In the general form, this can be greater or equal to C. Okay. And what is A? So A involves our constraints. So the rows of A's are determined by our constraint. So the first row of A, well, this is not an inequality this is an inequality constraint. So this is an inequality constraint. This is an equality constraint. An equality constraint is equivalent to y. So this guy here, y transpose x, y transpose alpha equals 0 is equivalent to y transpose alpha greater equal to 0 and y transpose alpha less equal to 0. Okay. Those two combined give you equals to 0. But y transpose alpha less equal to 0 is the same as minus y transpose alpha greater equal to 0. Okay. So an equality constraint becomes two inequality constraints, and then alpha greater equal to 0 is the same as I alpha greater equal to 0. So this matrix A, so we can identify the matrix A as y transpose minus y transpose, the identity n by n. So that's the matrix A. Okay. And the vector C is just all zeros. So C is just 0, 0, and the n-dimensional 0. Okay. So here, for the quadratic program in vector form that's equivalent to the quadratic program we need to solve, we can identify the parameters Q, P, A, and C. Q, P, A, and C. So if you send this in, to your quadratic programming algorithm, QP of Q, P, A, and C, it's going to output U star, which in our case is just alpha star, which is alpha star. Okay. And if you plug in these matrices, so Q is equal to this matrix times its transpose. P is the negative vector of all ones. A is, Y, where Y is here. Okay, minus Y, so as a row, and then the identity, and C is all zeros. You end up with alpha equals to 1/2, 1/2, 1, 0. Okay. So solving the dual problem using a quadratic program assigns alpha equals 1/2, alpha equals 1/2, alpha equals 1/2, alpha equals 1, alpha equals 0. Okay. And now we're ready to get our weights and our bias, okay, using this formula. Okay. So erase. Now that we've gotten our optimal alpha star, we don't need anything else. Okay, we've solved the problem. All we need is the alpha star. And so this implies that our weights, W star, is, the sum over my Lagrange multipliers, alpha n star, yn, xn, which is equal to 1/2. Okay, so that's alpha n star. Yn is -1 dot -1. Xn is just 0. Okay, plus 1/2. Yn is -1. Xn is 2, 2. Plus alpha n is 1. Yn is +1. And xn is 2, 0. Plus alpha n is 0. Okay, times yn, which is +1, times 3, 0. But 0 just gives me 0. So this is just 1/2, -1/2, 2, 2. Plus 2, 0, which is -1 plus 2, which is 1 minus 1. So those are my optimal weights. We can pick a positive alpha, a support vector. So pick a positive alpha, pick a support vector to get my bias. So B star. So we can pick the positive Lagrange multiplier alpha 1 is equal to Y1, so -1. Okay. Minus my optimal weights, 1, 1 transpose times the vector, which is 0, 0. So minus 1 minus 1 times 0, 0, which in this case, because this is 0, 0, that just gives me 0, 0. So this is just -1. So my classifier, G of x, is equal to W star x, which is x1 minus x2, sine of W star x, which is x1 minus x2, plus B star minus 1. Exactly what we got before. Okay. Now, I highly encourage you to work by hand through this example, plug it into the quadratic program, get 1/2, 1/2, 1, 0, okay. Obtain your optimal weights and bias, and convince yourself that this dual version of the problem is exactly analogous in the sense that is equivalent to, in the sense that if I solve this, I can get the solution to the primal form. Convince yourself with this small example. Just do it by hand. Okay? And that essentially is the algorithm for solving the optimal hyperplane problem in the dual version. Now, I'm going to erase and show you why this is magical, why this is relevant to being able to run, the nonlinear transform in infinite dimensional spaces.